Okay, good morning, everybody. Hopefully you can all hear me and you can see the slides. So it's 10 o'clock. I'm going to get cracking very punctually this morning. I'm aware, obviously, it's Armistice Day today, so I will try and have everything wrapped up by 11 o'clock so we can do the 2-minute silence. And obviously it will mean there'll be a little bit less time for questions than maybe we'd normally have, but obviously there's always the option to drop us an email or give us a call if you do have any questions that we don't get to in the session. So without further ado, let's get going. So today's webinar is about underfloor heating and radiators. My name is David Reid. I am one of the mechanical and electrical design engineers at Mesh Energy. And so I tend to take projects from the stage where they've completed feasibility through to a sort of tender specification type stage. That's my role. So I tend to get a little bit more into the detailed design than a lot of my colleagues do. So if I actually click on to the presentation, that will help. So what we're going to cover today is a quick introduction to Mesh Energy, and then a little section about why we should care about heat emitters. And this is something that that a lot of you might be asking. Well, you know, surely a radiator is a radiator. Why should we care? You know, underfloor heating works or it doesn't work. Again, why should we care too much? You know, as architects, why does it matter that we get this stuff right? Then some basic theory about how the systems work. A little bit about thermal comfort, the different types of sort of heat dissipation through the room, heat transfer, a little bit about flow temperatures and about what they might do. And then finally, a little bit about space considerations and controls. And this is kind of divided up into a section about underfloor heating and a section about radiators. So we'll cover sort of all that in each of those. So again, similar kind of thing with radiators. So, and then finally, we've got a bit about next steps and how you can work with Mesh Energy, and then a section for questions. Obviously, I'll make sure we finish that just in advance of 11 o'clock. So as I say, there's quite a lot to cover this morning, so I will run through this slide quite quickly. I'm sure most of you are aware of who Mesh are, but just in case you aren't, we're an independent consultancy. And we look to partner with architects and clients to basically demystify the quite complex market for renewable technologies. So we aim to produce to give people pride in their sort of low carbon projects and really just give, you know, sort of no nonsense approach to delivering those projects. So why should we care about heat emitters? Well, there's 5 good reasons here. The first of all is if we get it right, we can keep costs down. That's both the initial capital cost and also the running cost. We want to make sure that the building we're building is actually comfortable for people to live in or to work in. We want to make sure that the system is efficient. I mean, there's, you know, that's kind of ties up with the running costs. We want to give controllability. Nobody wants to be too hot or too cold. Again, that kind of links up quite nicely with the comfort. And also, we want our buildings to look nice. You know, there's nothing, you know, we could design a brilliantly engineered heating system, but if it looks awful, then nobody's going to want it in their building. So let's have a look at those in a bit more detail. So first of all, cost and efficiency. So we've got sort of 3 elements to that, really. We've got the initial capital cost, and we'll look at a little bit about each of that for underfloor and for radiators. I'm not going to go too much into fan convectors or any other types of heating system today, so sort of radiant panels or anything like that, simply because of time. We are looking at doing another CPD masterclass, which looks at some of the other types of heat emitter. We're going to concentrate on the 2 sort of big ones, underfloor and radiators today. Running costs, obviously we want to keep running costs of systems down. We want people to be warm, but we don't want spending all their money on heating. And obviously we want to, as a sustainable consultancy, we want to be driving down CO2 emissions. So again, that's sort of part of the project. CO2 emissions and running costs often go hand in hand as well. So if we can reduce running costs, we reduce CO2 emissions, and equally, if we reduce CO2 emissions, we can reduce running costs. Then we've got the design side, so the aesthetics. We're wanting to produce buildings with lots of good usable space that can be configured in multiple ways, and heat emitters can be a barrier to that. So we need to think about how the space is going to be used. We obviously want the aesthetics to be correct for the environment. There'd be no point in having horrible, ugly radiators in a beautiful, high specification home. And equally, there'd be no benefit to having very, very high-end underfloor heating in a building where it wasn't required, in a factory or something. So it's getting that balance right. And finally, of course, controllability. We want the system to be controllable. And then obviously the comfort. We want to get the actual room temperatures we require. We want to get good perceived levels of temperature, and that's something we'll look at a bit in the next slide, because actually the temperature you perceive and the temperature a room is actually at might not be always the same thing. And then we also want to look at how temperature varies within a space, especially around areas of high heat loss, such as windows. So that's so if you've got big glass areas in a building, that can be an area of high heat loss. And also a little bit about indoor air quality, because heating can influence indoor air quality. So here's our room, and we're looking at three sort of heating systems there. So in this graph on the left-hand side, you can see the typical temperature gradient for a room heated with underfloor heating. So you can see fairly obviously, because the floor is warm, the warmest temperatures are at the floor level. And then as you go up, there's a relatively even temperature gradient. And then just below the ceiling, it dips off a little bit because the ceiling acts as a little bit of a heat sink. Then in the middle, you've got your idealized heating system. And then in an idealized heating system, you'd have an even temperature gradient all the way up to the ceiling. And basically, once it's above head height, then you can't feel it, so it doesn't really matter. And then finally, we've got the temperature gradient you'd get from a radiator system. And because radiators tend to work a bit more by natural convection rather than radiative heat, so they're actually very badly named. They should really be called convectors rather than radiators. The room temperature will fluctuate quite significantly across the room. So you'll get the lowest temperatures at the floor level and then the highest temperatures up near the ceiling. So how does this then compare to how people actually want a room to feel? Well, actually, most people prefer to have warm feet and a cool head. So if you look at the studies that people have done where they've compared perceived comfort versus temperature, in most cases, people will prefer to be slightly warmer down at their feet and then slightly cooler at head level, which obviously is the opposite of what you get with a radiator, and closer to what you get with an underfloor heating system. Underfloor heating does tend to produce more closer to that idealized even temperature throughout the sort of different levels in the room. But reducing the temperature gradient also allows us to lower the room temperature, and that has an advantage both from a comfort point of view, but also obviously lowers energy bills because the average temperature is lower, so the heat losses are lower. So from all those points of view, it's looking like underfloor is probably going to be the best option, but we'll get onto that in a little bit more detail later on. So before we start looking at any heating system, I would always go back to this energy hierarchy, and you've probably heard all of us drone on about this diagram in many times. but it really is the absolutely crucial part of our of the system. So we must make sure that the building is as well insulated and low energy as possible before we start implementing nice high-tech heating systems. It's the cheapest way of doing it. It's the longest lasting way of doing it. Any improvement you make to the building at design stage before you start looking at the heating system will pay dividends for the entire life of the building. Whereas the heating system will only last as long as the heating system lasts, and that might be a quarter of the lifetime of the building, it might be half the lifetime of the building, but it's going to not be the whole life of the building. Added to which, high-tech heating systems are expensive, insulation and improvements in the actual fabric are generally pretty cheap. So just to sort of reiterate that point, any heating system will perform better in a well-insulated home. And here we've got a home which is being upgraded with lots of insulation all around it, creating a nice warm box that we can then start applying our high-tech heating system to. So let's have a little look at sizing and heat demands. So, oh look, we've gone back to let's improve the fabric first. Well, okay, we've done that. Then we need to determine the design temperature based on the location and elevation. So that is actually something you can simply look up. So if you put the postcode into a sort of subsea calculator, it will tell you what the design temperature is. Typically in England, it's somewhere between about -2 and -4. Scotland tends to go down a little bit lower than that. Wales, again, maybe a little bit lower than that. But that's the sort of outside temperature you're designing the building to stay warm at. Then from that, you can then determine the peak heat demand. And you do that based on standard air temperatures in the rooms. So that is generally 21 degrees for living areas, 18 for bedrooms, 22 for bathrooms, and 18 for kitchens and WCs, and utility rooms and rooms like that. So you then work out what your total heat loss is. You put it all into an Excel spreadsheet, add it all up, and you should end up with a peak heat demand, which you can then divide up on a room-by-room basis to determine what the specific heat load is, which is measured in watts per meter squared. And that is something you definitely need for underfloor heating design, because obviously your floor is your heat emitter, and so it's quite important you know from your floor area what heat you're trying to get out of it. So let's have a little more look in detail at underfloor heating. So underfloor heating works primarily by radiation, whilst radiators work primarily by convection. Very confusingly. So we've got our floor that might be at around sort of between 24 and 29 degrees, quite typically. But the underfloor heating system gently warms the entire floor. It's not a sort of point heat like a radiator is, or an open fire is, or a wood burning stove or something. But basically the heat is distributed by a series of pipes that have warm water circulated through them. There is also electric underfloor heating, where you have effectively electric heating elements in the floor. We're not going to cover that in this CPD. We're looking at wet underfloor heating systems, so where water circulating through pipes. And as I said, the majority of the heat transfer comes from radiation rather than convection. And what that means as somebody who's actually occupying that room, it means that when you walk into the room, you will instantly feel warm, because your body will feel that heat being radiated from the floor. So how does it actually work? Well, here's a sort of cutaway of a typical underfloor installation. So we're distributing warm water to each zone through a manifold. So we'll have a look a little bit more in the detail of what these components are in a second. Each zone is controlled by its own thermostat, and that opens and closes the valve that allows water to go to each zone. And here's a little bit more of a sort of cutaway. So here's our manifold. These little white knobs on here are the little control valves. In fact, it might be the red ones. So you have that. Then you have the underfloor heating pipes, and this would serve several rooms, this manifold. So it will go off. So some of these pipes will go off to other rooms. Some will be laid straight into this room. And then you have the floor finish over the top of that. And there's obviously lots of different floor constructions that we're going to look at, which, but the basic principle is always the same, is you've got warm water going through some pipes which are warming the floor up. So what are the benefits of underfloor? So because it has the lowest flow temperatures, because you've got the biggest area that you're trying to get heat out of, it gives the best seasonal coefficient of performance, or SCOP, from heat pumps, and the highest efficiency from condensing boilers. Boilers can run in condensing mode more of the time, so you get a slightly better efficiency from the boilers. Because it transmits most of its heat through radiative heat rather than through convection, it does give a greater level of comfort and well-being than radiators. It does give probably the greatest flexibility in terms of room design. Once you've got your underfloor in, obviously there's no radiators to worry about covering up. There's no sort of hot and cold spots in the room. You don't have to worry about air circulation. You don't have to worry about drafts, those kind of things. Because you're not relying on convection, you're not moving as much air around in the room, so you're not creating convection currents in the room, which means there's less air and dust movement. That might be important if you've got somebody who's, for example, got particularly bad allergies to dust. So that can be a little bit of a selling point as well. It is compatible with most floor finishes. There are very few floor finishes you can't use with underfloor. But as with anything, there are also some downsides as well, some disbenefits. So underfloor heating is pretty expensive to retrofit. Because it tends to have a much higher thermal mass, it can be a little bit slower to respond to inputs from the controls. If you've got a particularly old property where you've got very low ceiling heights, retrofitting underfloor heating will tend to raise the floor heights a little bit, and then hence reduce that ceiling height even further. So that's something just to bear in mind if you're looking at very old properties. But there's not actually that many disbenefits to underfloor. The main one is really the cost, and that's why people tend to shy away from it in some circumstances, especially in the retrofit market. So heat outputs from underfloor heating. Well, the heat output will vary with lots of different design considerations. So the actual floor construction, and that drives the type of underfloor heating system that's chosen. The floor finish itself, so typically, if you imagine floors that feel cold to the touch initially, will tend to work better with underfloor heating than the floors that naturally feel warm to the touch. And that's because floors that feel cold to the touch are actually conducting heat away from your skin, hence the feeling of cold. Floors that feel warm to the touch, such as carpet, they're good insulators. So not only do they hold heat in the room, but also they stop heat coming out of the floor into the room. So floor finishes such as stone and tiles and those kind of floor finishes tend to work really, really well with underfloor. With carpet, you have to be a little bit more careful. Pipe spacing. So if you the spacing between the pipes can be varied, and the closer you put the pipes together, the higher the output of the underfloor, but obviously the greater the cost of installation. And if you move those centers further apart, then you reduce the output of the underfloor heating system, but obviously you also reduce the capital cost of installation. So this is again where getting that room by room heat loss absolutely spot on is really crucial. The desired room temperature, it's simply physics that if you're trying to transfer heat from one place to another, you need to have a driving temperature difference. So if the room is warmer, then you're going to get less heat out of your underfloor heating system than if it's cooler, because the rate of heat transfer will be lower. And finally, the system flow temperature. So that kind of ties in with the previous one. If you make the water hotter, then you get a higher, faster heat transfer. If you make the water colder, then you get a slower heat transfer. The delta T effectively tells you what the average temperature is across the water in that floor, and then that works back to what your heat output is. So you can see there's sort of 5 different things there to take into consideration when you're designing the underfloor. But if you know, they're all well understood things. They're all things that you can easily look up. They're all things that you can easily model. So we can get to a pretty good answer fairly easily. So when should you seek expert advice? So if you want really high room temperatures, then it's best to seek expert advice, for the simple reason that most floor finishes have a limit on the floor surface temperature, and equally you can't go too hot because it will simply be uncomfortable to walk on a floor which is more than about sort of 29 or 30 degrees. So if you want high room temperatures, because of that lack of driving temperature difference, it's probably best to seek expert advice. If you've got a solid floored room, so a concrete floor or a floor where the room heat loss is more than about 80 watts per meter squared, then it's best to seek expert advice. You can get underfloor to work up to about 100 watts per meter squared, but really you need to be looking at the fabric if you're approaching sort of 80 watts per meter squared anyway. So that's where maybe a fabric optimization exercise might be useful. And timber floored rooms, because timber doesn't transmit heat quite so well, it's probably best to get some advice if you're looking at more than about 50 watts per meter squared, and that's sort of typical of sort of 1980s type houses would be sort of in that sort of 50 watts per meter squared kind of realm. Anything built earlier than that without fabric improvement is likely to be a little bit higher than that. And the other one is if you've got large areas which will be covered by rugs or furniture. Again, simply because rugs and furniture act as insulators, so they stop the heat coming out of the floor. So fairly obviously, you know, the sort of obvious ones are things like kitchen islands, large thick rugs, very large sofas, those kind of things, or large sofas in small rooms, built-in furniture, those kind of things. I've got a couple of questions here. I've got a client with a solid concrete floor and no budget to cut into it to fit pipework. Is it reasonable to suggest electric heating mats, or is this definitely not environmentally acceptable? There is insulation below the floor because it's 1920s apartment block. Okay, so the best advice I would give to that is you're probably going to be best off looking at low flow temperature radiators for the best solution to that, and improving the fabric as far as you possibly can in terms of the walls and ceilings and windows. So that would probably be my sort of first stop with that one, rather than going to underfloor. The running cost of electric underfloor heating mats is likely to be prohibitive. The electric underfloor heating mats are really good in rooms with very small areas where you maybe want to have that room heated at a time when the rest of the building isn't being heated. Typically they'd be used in bathrooms, for example. So hopefully that answers that question, Anna. So here's a little thing about these are the three sort of most common constructions of floor that you probably find on a sort of new build or retrofit type situation. There are lots of other variations. Just from a time point of view, I'm not going to try and go through every single one. So we're just going to look at these three. So if we start with the first one, this is a solid concrete floor with a screed top. You'll see that typically the pipes are laid on top of insulation and clipped to the insulation before the screed is poured, and then the floor finish is applied over the top of that. The Upsides of this system is that you do get really nice even heating from the floor. Screed, if you select the right Screed, works really well to sort of pass the heat, also sort of conduct the heat through the floor, give you nice even floor covering, floor heating, and you get a good amount of radiant heat out of it. The downside is because you've got quite a lot of thermal mass in this system, it can be a little bit slow to respond. And obviously it's a wet trade when you actually come to actually fit this, so it might not be suitable for all buildings. So let's have a look at the sort of dry alternative to that. So where you've got a nice flat subfloor, and the standard for that is usually SR2, which and Tom from Warmerfloor who I know is listening into this, will probably shoot me if I get this wrong, but I think it's something like 5 millimeters difference over a certain length. So basically you want a nice flat subfloor, and this is where you would use a dry construction sort of floating floor system. And this is one of the common ones where you have a grooved insulation board which you lay over the top of the subfloor, and then you lay your floor finish over the top of that. That insulation board was probably going to be aluminium coated as well. That helps spread the heat from the between the pipes, so you get as even a floor temperature as possible. Gives a slightly faster response than an in-Screed system, but it's a good option where you don't have the option for pouring Screed. Tom's just said that's right, so I got it right. Thank goodness for that. Okay, so and finally we'll go back to the next one. So this is the type of situation you might well find on a first floor. A lot of architects shy away from specifying underfloor on the first floor of buildings, thinking it's going to be too complicated. It's really not. So this is a diffusion plate system. So you've got your floor joists, and you run your pipes in parallel with the floor joists, and then you have the aluminium plates that sit between the joists, and those aluminium plates conduct the heat between the pipes, and then allow a nice even floor temperature. So typically this will give a slightly lower output than an in-Screed system, but because it's low weight, it does give and low thermal mass, it does give a pretty fast response. So it's good, especially if you've got a well-insulated building and you're looking to put first floor underfloor heating in. So that's quite a popular solution. So those are the three common ones. As I said, there are umpteen different types of variation on that, and it's worth talking to an underfloor specialist to get the lowdown on exactly what's going to suit your project. Obviously, that's what we kind of do on a day-to-day basis at Mesh. So that's where we can help you. So in terms of floor finishes, loads of different floor finishes that are available, but basically underfloor can be used with pretty much anything. So tiles, wooden engineered laminate flooring, vinyl, carpet and rugs. The one thing I would say is with carpets, it's just worth sort of thinking about the TOG rating on the carpet. So that's usually a number you can look up quite easily from the manufacturer's data, but you're looking for something that's below 2.5 TOG. Ideally below 1.5 TOG, but 2.5 TOG is the absolute maximum. So you don't want really thick, Austin Powers style shag pile carpets, because it will basically act as a sort of jacket over your underfloor heating, stopping the heat getting into the building. Obviously, low thermal mass, high conductivity floor coverings will give the fastest response. So things like slimish tiles will give really fast response. You may find that particularly with wooden floors, there are limits on the water content of the floor, and there might well be limits on the surface temperature you can get on some floorings. So again, it's just worth seeking expert advice. In most cases, if you've got your insulation really up to a really high spec, then you won't need a high floor temperature to get the heat output you require. So it's all this, it always goes round in these swings and roundabouts. You improve the insulation. If you improve the insulation, you don't need so much heating, so you get lower capital costs. But not only that, but you can then run the underfloor heating at a cooler temperature, which then means you get an advantage on your COP from your heat pump, or you'll get a better efficiency from your boiler. So again, it's this sort of cascading benefit that you get from better insulation. So let's have a look at some controls. You can see the picture here of a fairly typical room thermostat, telling us that the room is at 20 degrees C. It's a Monday morning, and then the little sort of flame icon tells you that there's a heat demand. So typically underfloor would be controlled on a room by room basis. So those of you who are used to gas and radiator central heating systems, you might have one or maybe two thermostats around your house, two zones. But underfloor, you tend to have a thermostat in each room. It will have its own set temperature, own setbacks, and it can be enabled to save energy at periods where the room's not being occupied. So typically what you do with underfloor is you keep the room relatively warm most of the time, but maybe overnight you'd set the temperature back, maybe from 21 degrees in the living room down to maybe 15 or 16 or 17, just to save a little bit of energy. But then when you go in again in the morning, the room's already heated back up and it's all nice and warm for you. So it's warm when you want it to be warm, and you're not overheating. And you can also use floor temperature thermostats where you've got limits on the floor temperature. There's a question here from Paul saying, does the 2.5 TOG assume, does that include the underlay for any carpet? Yes, it does. Yeah, that does include the underlay. But as I say, you really want to reduce that TOG rating as far as you can, because it will make the system more effective. And again, if you've got a low TOG rating on your carpet, you might then be able to reduce the flow temperature a little bit, and that then has the knock-on benefits with COPs on heat pumps and things. Thanks for the question. Okay, so we're just going to look a little bit more at some advanced controls now. So this is actually quite an old picture, because you'll see it's a Nokia phone running Windows, which is got to be a few years old now. But it gives you an idea that you can control with some more advanced heating controls, and there's lots on the market. You can remotely control the room's temperatures from your phone. You can maybe switch the heating on before you get home. You can set it back when you go away. Some controls will also do things like they'll allow you to set the time you want the room to be warm for, and it will then adjust the heat up time depending upon the ambient temperatures, and use a little algorithm on that, which is quite a nice little thing. So again, you're not having the room heating up too early or too late, so it's not cold when you go in there, but equally it's not warm when you don't need it to be. And also things like holiday modes can be used, because holiday modes are really useful for periods when you're away from home. So there's a question here from Simon about time lags. So you're quite right, because of the greater thermal mass in an underfloor heating system, what you tend to do is you tend to advance everything a little bit more than you would with a radiator system. So for example, if you want your living room to be warm at 7 o'clock in the morning, with a radiator system you might turn the underfloor the heating on at 6, whereas with underfloor you might turn it on at 5, but equally you know that you go out by 9 o'clock in the morning to go to work. So instead of having that setback start at 9 o'clock when you go, you could set that back to 8 o'clock, because the thermal mass will keep the room warm for that bit longer. So yeah, you're effectively sort of shifting when you're using the controls. But also some of the, as I just mentioned, some of the smarter controls can actually do some of that work for you by learning how the system responds and how room temperatures respond at different ambient temperatures. So hopefully that answers that question. Okay, so let's go on to radiators. I do feel like I'm running through this really quickly, so apologies if this is just seeming like way too much to take in. I'm hoping you guys have got a pretty good handle on a lot of this stuff already, so hopefully this is sort of reinforcing some existing knowledge rather than being all completely new. But we will have some time for questions at the end. So let's have a quick look at the benefits of radiators. There's a question from Claire about underfloor heating for schools. I'll come back to that at the end if that's all right, Claire. So benefits. Radiators are great where you've got a retrofit, where you've got an existing system, and they're cheaper to install. So if you're trying to build down to a cost, then it might be a cheaper option than underfloor. Obviously, you get a full choice of floor coverings. And although I did say, underfloor is compatible with almost all floor coverings, there are a few where it's a bit more problematic. So it does give you that full choice. It's obviously suitable for those rooms where you had lots of rugs or furniture or a very thick carpet was wanted, where underfloor is not going to work quite so well. And they do tend to give slightly faster response time than underfloor heating. Another one that was brought up to me the other day was that radiators can be more practical in some applications, and the example that was given to me was care homes, where perhaps you'd get some spills that might be difficult to clear up, and might smell fairly unpleasant if they were heated over a long period of time. So from that point of view, there might be radiators might be better in those applications. What are the downsides of radiators? Well, they tend to run higher flow temperatures than underfloor, so that leads to slightly lower coefficient of performance from heat pumps. Because you require wall space, that can reduce the design flexibility. So whilst it might increase the design and flexibility of what you can do on the floor in terms of furniture and rugs and those kind of things and carpets, also it might limit your furniture layout, because obviously you can't block radiators and want them to work effectively. And if you do want to lower the flow temperatures, you have to increase the size of the radiators. I would say this can be offset by specialist low flow temperature radiators, but they're a bit more expensive. And because of the effect we talked about earlier, with the radiative, the way that the radiators tend to produce most of their heat through convection rather than radiation, some people will find rooms heated with radiators a little less comfortable, which leads me rather nicely onto this slide, showing how a radiator heats a room. So it effectively creates a natural convection current going around the room. So cool air comes into the bottom of the radiator, is heated as it goes through the radiator, exits through the top of the radiator, rises up towards ceiling level, and then cool air at the other side of the room sinks down to the bottom of the room and is drawn across towards the radiator, is then heated. So you get this sort of cycle. And by strategically placing radiators, especially around areas where maybe you get more cold air coming into the room, so maybe by external doorways, windows, those kind of things, you can reduce the feelings of discomfort. So I've kind of covered all that. The only other one to mention is that one at the bottom about air and dust movement. Because obviously you're creating air movement, it can cause dust to be picked up. So you will tend to get slightly better indoor air quality from underfloor rather than from radiators. There's a question from Anna about the manufacturer of the radiator in the photo. I think it's a Jager, but I'm not 100% sure. I'd have to check where I got that image from, but I think it's a Jager radiator. So here's a little sort of very simplified diagram of how radiators work. So basically, hot water is distributed around the house in sort of two parallel pipes, one going towards the boiler called the return, and one going away from the boiler called the flow or the heat pump. And very simply, those two parallel pipes are connected to each other through the radiators, and the radiators allow water to go through them or don't allow water to go through them, and that's controlled by a TRV, which is a thermostatic radiator valve. And so once the room's up to temperature, that valve closes and prevents water going through the radiator. So people think that if they turn the radiator up to 8 on the thermostatic valve, it's going to make the room heat up quicker. It's not going to make the room heat up quicker. All it's going to do is mean the room overheats when it does get up to temperature. So you can turn that radiator valve. You want to set that radiator valve once at typically between sort of 3 and 4 gives a nice room temperature, and it will simply turn on or off. It's not a sort of mid-position valve. It is either on or it's off. And once it gets up to temperature, it will turn off. And once the room temperature drops, then it will open again and allow water to flow through again. So how is the radiator output determined? You'll see there's quite a common theme here with the underfloor, but basically it's a combination of flow temperature, return temperature, room temperature, and radiator surface area. So much the same physics as we had with the underfloor heating. So just to explain that a little bit more, the flow and return temperature, if you I think actually I do cover this later on, but the flow temperature and return temperature tell you what your average temperature is in the radiator. The room temperature then tells you what your difference between the radiator temperature and the room temperature is going to be. That gives you a driving sort of temperature difference. And then the surface area, the larger the surface area, the greater the heat transfer. So this is a question we frequently get asked at Mesh, which is about retrofitting heat pumps to an existing radiator system. And the answer, unfortunately, we have to give is it may be possible. So here's our new heat pump. This is a pretty funky design from a company called Red, who are based over in Northern Ireland. The first place we'd always say is start with the fabric of the building. So have we upgraded the fabric of the building to reduce the heat loss? If we have, then we've already effectively moved the radiators from being correctly sized to being oversized. So that's sort of step one. Then we need to check the sizing of the existing flow radiators and how they're performing at the existing flow temperatures to check whether the radiators are going to be suitable. Then we look at the condition of both the radiators and the pipework. And finally, we look at what the seasonal coefficient of performance we actually want from the heat pump is. Now, obviously, the answer to that is going to be the best possible. But if we have a limit on how poor we can make the seasonal coefficient of performance, then that will tell us what the limit on flow temperature is going to be, and therefore that then tells us what the maximum we could possibly get out of those radiators is, and whether they're suitable or not. If some of the radiators are suitable and some aren't, all is not lost though, because we may well be able to go with a little bit more radiator sizing and start by looking again at just replacing some key radiators around the house. So how are radiators actually sized? Well, the first thing that happens is the radiator manufacturer determines a nominal output for the radiator, and that's done to a standard BSEN 422 and at a delta T of 60. And this is where delta T's can start getting a bit confusing. Delta T is quite often referred to as the difference between flow and return temperature in a heating system. But this delta T is we're looking at the difference between the temperature of the radiator and the temperature of the room. So it's a different delta T from the one that we're normally used to. And you see that 60 degrees C is quite a lot, because if you've got a room that's at 20 degrees C for easy maths, that means that your radiator needs to be at 80 degrees C to give a delta T of 60. And at 80 degrees C is going to be pretty damn warm. So let's see how we handle that. So we then have to adjust the nominal output to account for the system's true performance. And this is how we do it. So we determine the heating system's average temperature. So that's the flow temperature plus the return temperature divided by 2. Then we determine the heating to the room. So that is the system average temperature minus the room temperature. So that calculation we just did above. And then we apply a correction factor, and the correction factor is tabulated. So you simply apply the tabulated value, and typically it might be 0.7, 0.8, something like that. So if you divide the heat output that the manufacturer gives you by that correction factor, then that will tell you what the actual output of the radiator will be. And typically, you will always end up with a number that's significantly lower than the stated output if you're looking at low flow temperatures. So what other ways are there around that? Because if we just keep on making radiators bigger and bigger and bigger to increase their performance and lower flow temperatures, then we end up with effectively creating a sort of complete wall heating system. So there's lots of ways you can do that. You can increase the surface area of the radiator, and this is what these modern low flow temperature radiator designs do. Is they use higher they use different metals. So typically most radiators are made out of steel, which has a relatively low thermal conductivity. If you change the construction from steel to aluminium, then you can get much better conductivity. So that allows you to slightly increase the output of the radiator. You can also make the aluminium fins thinner, and then stack them so you increase the surface area of the radiator, and that allows you to reduce the wall space for a given output. It also allows you to get higher outputs from lower flow temperatures. And also because the other thing that these advanced radiator systems do is they reduce the amount of water contained within the radiator, and by doing that they give faster response times, faster heat up times. They can also give greater controllability. Again, that's down to the slightly lower amount of water in them. So we touched on controls of radiators a little bit earlier, and I talked about thermostatic radiator valves, and this is what a thermostatic radiator valve actually looks like inside. So how would you actually control it? Well, typically you'd start at the highest level with a 7-day timer, and that would simply enable or disable heating at different times of the week. Then you'd have a zone thermostat, so that would basically tell the boiler or the heat pump, is there demand in that zone or is there not demand in that zone for heating? And that's the thermostat on the wall that you'd be quite familiar with. And then finally, you'd have thermostatic radiator valves, and those thermostatic radiator valves would control the individual room temperatures. So how can we then take that to the next level? Well, there are lots of smart controls for radiators. This is the Eve system that's shown here, which is the one that's pushed by Apple as part of their Apple Home suite. But you can have smart zone thermostats, so that allows you to control a little bit more smartly, but also things like digital TRVs with remote access functions and those kind of things. So there's lots of things we can do with controls. Okay, fantastic. Well, that wraps up the technical content for this. So I'm going to give you a few takeaways now, and then a little bit about how this all fits into the Reba stages. So top 6 things to think about when you're choosing your heat emitters. First of all, fabric first. As always, we bang on about it time and again, fabric first. Improve the building as much as you can. We'd usually recommend installing underfloor heating if budget and construction allow for it. Bring the flow temperatures down as low as possible to ensure efficiency, especially from heat pumps. Match the emitter size to the peak load, the peak heat demand and the flow temperature. So that kind of 3 and 4 sit very much alongside one another. And if you can't use underfloor heating, then use low flow temperature radiators, because that will ensure the best possible efficiency. And finally, when you're designing your system, consider what the furniture layouts are going to be. So especially with radiators, so you can make sure that your radiators are fitting around where the furniture is going to go, and equally you're not blocking large areas of underfloor. If you can get all that, then you should have a very, very successful installation. Okay, so we've gone through all the technical side. Hopefully that was informative. So the next thing is how does that sort of fit into working with mesh? Well, typically we would sort of start a project from sort of stage 1 and look at a feasibility study and some preliminary energy and SAP calculations, and help with space and layouts drafting. We can do things like thermal design models at that kind of stage. Really sort of nail down how we can get this building as good as possible. So that's the sort of fabric first part, I guess, and the feasibility stage. Once we get to the detailed design, we can obviously do detailed design with you guys and help you out that way. And then when it comes to build, we can do tender review, installation oversight, and then finally the bit that people quite often forget, but also things like energy monitoring, air quality monitoring, those kind of things, post occupancy, are really important to the sort of successful project. Well, thank you so much for listening, everybody. If you have any questions, then please please drop them into the comments. I can see there's a few there already. So let me just scroll up a little bit.
Sorry, Dave, we also have next week's webinar, which is watch out for the biggest eco pitfalls with case studies.
Yep, that's an excellent one to go to. If we've had some we've come across a few disasters in our time and tried to unpick them. So yeah, well worth having a look. So I'm just going to go back to Claire's question she asked earlier about underfloor heating for schools. In new build schools, underfloor can be a really good option, partly because all the bits that can be damaged, so radiators and things like that, are kept well away. So actually it gives nice clean wall spaces for kids to use, and the sort of floor finishes in schools tend to be sort of quite work quite well with underfloor. So yeah, certainly schools are a good option for underfloor heating. So yeah, a good one for that. I think I answered Anna's question about the radiator. So then a question from Sarah about if we're looking to persuade a contractor to install underfloor heating with an air source heat pump rather than radiators due to space restrictions, do you have any advice on how the best way to do so? And really it comes down to from a contractor's point of view, there's always going to be this temptation to cut costs, and underfloor will tend to be a little bit more expensive than radiators. The way to do it is to look at the entire 20-year cost of installation, because when you factor in running costs for an air source heat pump installation where you've got radiators, the higher flow temperatures will mean higher running costs because of the reduced COP. So the way to do it is to look at the 20-year cost, and that's something that we routinely do in our feasibility studies. So that's probably the place to start, is by sort of trying to persuade them that it's good from a long-term cost point of view. Mohammed talking about copper piping versus plastic for underfloor. Go plastic. Avoid joints at all costs. You should be looking for pipes that have a 50 or 100-year guarantee on them. So there's some more detail to go into that. So then just go up. Then a question from Ewan. What's the optimum flow temperature for an underfloor heating system? It will depend upon the property, but a sort of good starting point is the lower the better. So what we would say is we'd say minimize your flow temperature to ensure that you get the output that you require, especially if you're going with a heat pump. Every degree you can knock off the flow temperature from a heat pump will give you an improvement of COP of about 0.02. So just as a sort of guide. So if you can decrease the flow temperature by sort of 5 degrees, and that's sort of 0.1 onto your COP straight away. So that's a sort of good rule of thumb. But basically, you're trying to reduce it as far as possible. Obviously, heat pumps will weather compensate as well, so they'll reduce flow temperature automatically as the weather warms up to help with that. Question from Mike. In a small apartment, can a combi boiler be used with underfloor heating? Absolutely. Yep. You'd then probably go for a mixed manifold rather than a unmixed one. So you'd actually mix some of the return water in with the flow water. But yeah, it certainly can be done. Again, if this is a new build, then maybe look at could you use either a communal air source heat pump system, or maybe even a ground source heat pump system with a shared collector, a sort of little micro box type ground source heat pump system, to move away from gas, if that was what you were wanting to do as well. So all of those are good options. What kind of radiator delta T would you design for an optimal air source heat pump performance? So in terms of delta T, probably no more than about 10 degrees for a heat pump. But again, it's more about reducing the flow temperature. And that again is that balance between the lower you make the flow temperature, the bigger your radiators get. And so you've then got a design consideration there. You can make the radiators bigger and bigger and bigger and reduce the flow temperature more and more and more, but then you end up living in a radiator eventually, which you don't want to do. Again, if you can, Alec, if you can go to underfloor, then I would say do so. If you can't, then look at specialist low flow temperature radiators. I've mentioned Yaga a couple of times, but they make an excellent range of low flow temperature radiators. A bit more expensive than a standard radiator, but good value. Question from Madeline. Underfloor heating is being used downstairs for the new build, MVHR and air source heat pump being used. Would you advise underfloor heating upstairs despite increased cost or ads and heat pads in bathroom? Honestly, if you can specify underfloor throughout the entire building, then I would go underfloor throughout the entire building. It's a good option. I'm just a bit wary of the time because we're a couple of minutes to 11. So yeah. Little answer here from Tom as well. It's about cross neutrality. So Tom, maybe we'll try and put you in touch with Sarah on that one. And quite a long question here from Joe. So Joe, what I might do is I might take that one offline and drop you an answer to that directly. Just conscious we're pretty much out of time. So guys, thank you so much for all your help and all your questions. We will pull all these questions off, but we've got about 30 seconds now until 11 o'clock. And obviously being Armistice Day, we should do our 2-minute silence. So thank you all so much, and I will see you on the next one. Thank you.